Welcome back to the Explainer. Today, we're going to crack a real classic from the coding interview world, LeetCode 189, Rotate Array. Now, this one looks pretty simple at first glance, but trust me, it's got this super elegant and efficient solution hiding inside. By the end of this, you're not just going to know the answer, you'll really get the why behind it, that clever thinking that makes it so cool. So let's dive right in.
All right, to really wrap our heads around this, let's forget about code for just a second. I want you to picture something. Imagine 7 people, and they're all sitting in a circle. We can just label them 1 through 7 to keep things simple. Okay, so they're all sitting there. Now, what if you told everyone, hey, get up and move 3 seats to your right? Where does everybody end up? Well, person 1 moves to where person 4 was sitting. Person 2 shuffles over to person 5's spot. You get the idea. But wait a minute, what about folks 5, 6, and 7? Since it's a circle, they can't just fall off the end, right? They have to wrap around and take those empty seats at the beginning. And that little wraparound idea, that is the absolute key to this whole problem.
So here's our game plan for today. We'll start with the problem itself, our shifting seats puzzle. Then I'll show you a really clever 3-step trick to solve it. We'll see that trick work with our own eyes, turn it into code, and finally, I'll give you some tips so you can totally ace this in an interview.
All right, first up, the shifting seats problem. Let's get a bit more formal and define what we're actually trying to solve here. So here's the official task. You get 2 things, an array of numbers and another number, k. And your job is to take every single element in that array and shift it k spots to the right. And just like with our people in a circle, the elements that would normally fall off the end, they've got to wrap right back around to the beginning.
Let's look at a solid example. Say we have our array 1, 2, 3, 4, 5, 6, 7, and we're told to rotate it by k equals 3. What should happen? Well, those last 3 numbers, the 5, 6, and 7, they need to end up at the very front. And the first part, the 1, 2, 3, and 4, just scoots over to make space. So our final answer, our goal, is 5, 6, 7, 1, 2, 3, 4.
Okay, next up, a clever 3-step trick. This is the fun part. So how do we actually pull this off? More importantly, how do we do it efficiently, especially without using up a bunch of extra memory? Well, there's a brilliant little algorithm for exactly this. Now, your first instinct might be, okay, I'll just move everything 1 spot to the right, and then do that again and again, k times, right? It seems logical. But what if k is a huge number, like 100,000? That's going to be so slow. It would time out for sure. Interviews are all about finding that optimal, smarter way to do things. And here's that smarter way. The most efficient, in-place solution is just 3 simple reversals. It feels a little like a magic trick. Step 1, you reverse the entire array. Step 2, you reverse just the first k elements. And step 3, you reverse everything that's left. That's it. I know it sounds kind of weird, but stick with me. Okay, time to see the trick in action. I know that 3-step process sounds a little random, so let's actually walk through it. This is where it's all going to click and make perfect sense. But hang on, before we dive in, here's a super important pro tip. Remember our circle of 7 people? If I asked you to move 10 spots, what would you really do? You'd move 7 spots, which puts you back where you started, and then you just move 3 more. So moving 10 is the same as moving 3. In code, we handle this with something called the modulo operator. We just say k equals k times modulo, the length of the array. It's basically finding the remainder, and it stops us from doing a ton of extra, unnecessary work. All right, let's lock in our example and get started. We've got our array, 1, 2, 3, 4, 5, 6, 7, and our k is 3. Just to remind ourselves, our final goal is to get 5, 6, 7, 1, 2, 3, 4. So let's see how our 3 reversal trick makes that happen. Step 1, reverse the whole thing, the entire array. So 1, 2, 3, 4, 5, 6, 7 becomes 7, 6, 5, 4, 3, 2, 1. Now look carefully at what just happened. The numbers we want to end up at the front, the 5, 6, and 7, they're now at the beginning of the array. They're backwards, sure, but they're in the right section. This is the first piece of the magic.
All right, on to step 2. Now, we only look at the first k elements, in our case, the first 3. So we take that 7, 6, 5 chunk, and we reverse just that part, and poof, it becomes 5, 6, 7. Would you look at that? The front of our array is now perfect. It's exactly where it needs to be. We are so close.
And finally, step 3. You guessed it, we just have to fix the rest of the array. So we take that remaining part, 4, 3, 2, 1, and we reverse it. It flips to become 1, 2, 3, 4. And that's it. We're done. Our final, perfectly rotated array. How cool is that? It's such a clever, non-obvious solution.
All right, section 4, making it code. Seeing it happen visually is one thing, but let's see what this looks like when we actually write it out. We're going to translate that 3-step logic directly into a function.
And honestly, the code is as clean as the idea itself. So inside our main rotate function, first things first, we get the length n. And we do that super important modulo trick to normalize k. Then you can see our 3 steps, plain as day. This first reverse call, from 0 to n-1, that's our step 1, reversing the whole thing. This second reverse call, from 0 to k-1, that's step 2, fixing the front part. And this last one, from k to n-1, is our step 3, fixing the rest. It's a perfect one-to-one translation of what we just saw.
Okay, last section, ace the interview. You've got the solution down cold. Now, how do you talk about it in a technical interview to really impress them?
Here's the most important thing to talk about, efficiency. Our reversal trick has a time complexity of O of n, which is great. It just means we have to look at each element a couple of times, but the work grows linearly with the size of the array. But the real win, the thing that makes this the best solution, is the space complexity. It's O of 1. That means we use constant space. We're not creating a whole new copy of the array, we're doing everything in place. Being able to explain why O of 1 space is better than the O of n space an extra array would take, that's what interviewers absolutely love to hear.
And when you're coding this up, probably under a bit of pressure, just watch out for these common little traps. First, always remember to normalize k with the modulo. It's so easy to forget. Second, be so careful with your start and end indexes for the reversals. Off by 1 errors are the classic enemy here. Also, don't forget to think about edge cases, like what if k is 0? Nothing should happen, right? And finally, be ready to explain why you didn't just go for that slow 1-by-1 shifting method.
And to leave you with a little challenge, now that you've totally mastered rotating to the right, how would you change things up to rotate the array to the left by k steps? I'll give you a hint. The answer uses the exact same reversal trick, just in a slightly different order. Give it a shot. It's a fantastic way to make sure this all really sticks. Thanks so much for joining me on The Explainer.